I don't know. Okay, quick reminder that if you haven't seen it, your next homework assignment won't be due until the Tuesday after we come back from spring break. So not like the Tuesday after spring break, but the one after that. So enjoy your spring break. This lecture? Yeah. So the title of today's, and I always swear I wanted to wear, whenever I give this lecture, I want to wear like a red and white striped hat. I don't have one. So today is Where's Newton? Where is Newton? After all, this class, general relativity, this subject, is a generalization of Newtonian gravity, and so we should be able to, somewhere in this complicated tensorial nightmare of curvature and geodesics and all that crap, we should be able to extricate good old Newtonian gravity. Okay? So, as usual, I will remind you that this topic, and in fact Newtonian gravity has analogs, has two parts. Okay, the first part is how space gets curved. And last time we learned that the curvature is governed by Einstein's equation, r mu nu minus 1/2 g mu nu r equals 8 pi g t mu nu. And then B is how does curved space influence motion. And today, since we're just trying to recover Newtonian gravity, we're not trying to incorporate electromagnetism or other forces, we only need the result from general relativity about how curvature influences the motion of particles that are only experiencing the force of gravity. And that, of course, I'm not going to do the cards today, I'm just going to pick people. And that, of course, is described by what, Kowalski? Motion in a curved space-time.
Is described by geodesics.
Yeah, the geodesic equation. So we can write down the geodesic equation. So we have some path through space-time x mu parameterized by some quantity. Right now we'll call it lambda. And then we combine that with some Christoffel, with a Christoffel symbol of appropriate indices. Okay? These two equations should be hiding somewhere in there Newtonian gravity. And when I say Newtonian gravity, I don't just mean the force of gravity, because that is certainly a part of Newtonian gravity, but I also mean Newtonian mechanics, i.e. Newton's second law, because after all, the motion of things is not just a force, it's a force used in Newton's second law to determine the acceleration. So we should be able to get both of those components of Newtonian gravity and Newtonian dynamics somewhere coming out of these two equations. Okay, so what might these look like in the non-relativistic limit? Well, the statement how space gets curved should somehow reduce to a statement about the force of gravity. Okay, and you can certainly write down the gravitational force law. Hopefully you can write it near the surface of the Earth. That was the first thing you learned in Physics 1. And you can probably write down the gravitational force law between two well-separated objects in terms of big G, m1, m2 over r squared. And we can beat this into that form, but it turns out that it's actually a little more direct to write down the Newtonian gravitational force law in a slightly more sophisticated format, and that is we can say that the gravitational force can be derived from a scalar potential phi by solving an equation of the following form. Del squared phi equals 4 pi g rho, where rho here is mass density. Okay? Now this should look a lot like one of Maxwell's equations, right? But in fact, you should expect that, because after all, the Coulomb force law looks identical to Newton's law of universal gravitation. So being able to sort of tease out the electrostatic behavior in terms of solving this equation, you should expect that doing gravitostatic calculations, you should be solving a similar equation. The source, instead of being charged, density is instead mass density. So we're going to be looking for this equation somewhere hiding in here, okay? And then for the motion, well, by the way, this phi, if I took the gradient minus the gradient of phi, that's exactly going to be this thing we call the gravitational field, in the same sense that the gradient of the scalar potential in electromagnetism gives you the electric field. Here we're doing gravity, so this should give me the gravitational field. And then we can immediately figure out the non-relativistic statement for how things respond to gravity, and that's Newton's second law. But we already know that the mass doesn't really play a role because gravitational and inertial mass are the same, so we can just say that the acceleration of an object is minus grad phi. Okay? That is, the acceleration is just g. So somehow this expression we should be able to tease out of this expression, where the curvature of the space-time that you're getting here is going to appear in this expression through the Christoffel connection, because remember this guy right here depends on the metric. Okay? So our job today is to just beat these equations into a form where somehow we can identify these two non-relativistic expressions. And what you're going to find is you throw away a lot of GR to get there, which in turn tells us GR is much richer than Newtonian gravity, which is what we would have expected. Okay, so we need some limits, and I'm going to erase this in just a minute, but let me just write down the two goals. So we've got del squared phi is 4 pi g rho, and then A is minus del phi. And we should expect that in going from this full-blown GR treatment down to this sort of non-relativistic version, we should be able to apply some kind of limits. All right, so let's go through what those limits are going to be. And I'll refer to these throughout. So the first limit is going to be small velocities. You know that when we go from any relativistic theory to a non-relativistic theory, typically we limit ourselves to small velocities, but I'm going to write this in a very particular way. The velocity of an object, and this is just good old spatial velocity. This is like how fast you're moving along spatial directions with respect to time. We know that the spatial velocities have to be much, much less than c, but c is in this class now 1. So dxi dt has to be much, much less than 1. But I can actually take this statement and turn it around and say that means dxi is much, much less than dt. Okay? If at any point I say something like, where'd you get that? Just raise your hand and say, where'd you get that? Okay? But I can take this and write something useful that you can already see we'll probably make use of this later on. I can divide both sides by the same thing to say that any dxi d lambda is going to be much, much less than dt d lambda, and you can see where we're going to start being able to apply that in working with the geodesic equation. Okay? So small velocities. And then we need a weak gravitational field. If we have a very strong gravitational field, that is sort of measured by the fact that the curvature changes rapidly as we move a small distance. So if we want a weak gravitational field, then what we can do is we can take the metric of our space-time and we can approximate the metric by saying we essentially have flat space. Gravity isn't really curving things very much, but we don't have flat space, we have a little bit of a correction to it. And we're going to call that correction h mu nu. Okay? So this is, of course, flat space metric with Cartesian coordinates. So everything I'm going to talk about is predicated on us using Cartesian coordinates because I wrote eta as the metric I'm starting with. These are small fluctuations. And this is the full metric of our space. And by small fluctuations, what I have in mind is that the magnitude of these fluctuations should be much, much smaller than 1, and also the derivative of these should be much, much smaller than 1. okay? And what this will allow us to do is, in our calculations, it will allow us to ignore anything that's order h squared or higher. Where by h squared I also mean dh. So I can ignore things that have h squared, hdh, dh squared, and then any higher power, okay? And then the last condition is, and of course Newtonian gravity is a static theory of gravity. It can't accurately describe what's going on if you've got masses that are moving around. So we need a static gravitational field. Spelled today. Static gravitational field, and mathematically that's going to mean that the time derivative of our metric is 0. Okay? Now, I mean, you don't have to take this limit. You could just take these limits, and then what you would end up getting is a time dependence, or an approximation to Newtonian gravity, including like gravitomagnetic effects. But we're not really interested in that, in the limit that we're, or in the connection that we want to make today. Okay, so with all that in mind, we're going to immediately find one headache, and that is that B immediately forces us to work with something that's a little weird, and that is that the inverse metric, when we need it, is going to take a funny form, okay? So one of the consequences of B is that the inverse metric, now you might say, oh, if this is the metric, then I might guess that the inverse metric would just be eta mu nu plus h mu nu. Seems pretty reasonable, right? It doesn't?
No.
I mean, that would be my first guess. But it's not right. It's not right. It's actually a little more complicated than that. So the inverse metric actually turns out to be eta mu nu minus eta mu alpha, eta nu beta, h alpha beta. Okay. Now let me motivate why that's the case. Okay. So just running very quickly through this argument, but that's the key result, is that that's our inverse metric. So this is our metric expanded around flat space. This is our inverse metric expanded around flat space. Now let me support that. So first of all, we know that if we have the metric and we contract it with itself, then this has to give us a delta function. I'm summing over mu there. So this we can kind of take as the defining feature of the inverse metric if we start with a metric. So this is, we're starting with this. We know the expansion of the true metric. We want to use this relationship to try and tease out what this should be. Okay? So if I actually just plug in the two expressions that I've proposed, so the metric, lambda mu nu plus h lambda mu, times the inverse metric, and now getting my indices to match up. I should really look at my paper because I'm never going to get this right. H alpha beta, there we go. Okay. And now I just factor this thing out, or distribute this thing out. So we're going to have eta lambda mu, eta mu nu, and then I can take this guy and just write it down, and then I'll explain what I did. It still smells in this room. Okay, so h lambda mu, eta mu nu, that's that guy right there. This guy comes from hitting this guy onto that guy. And then the last term is order h squared, and I know I'm going to ignore that. Okay, so ignore this. This guy is just going to give me delta lambda nu. And then this guy, so mu mu mu. This is going to become a delta function on lambda alpha. Did I do that right? Lambda alpha, mu, beta, alpha, beta. I feel like I don't have this right. Mu, lambda.
Are deltas commutable?
Yeah, no, I can move this anywhere I want. So, yeah. No, no. Wait, I can use this. Hold on, let me just do it. I'm confusing myself. All right, I'm going to use this to change the index alpha to a lambda. So now I'm going to have eta nu beta h lambda beta. Yeah, that's fine. Okay, and then plus eta mu nu h lambda mu. Well, these are just dummy indices. They're summed anyway. All right. This guy is symmetric, so I can flip it around, and then those two terms cancel. Okay. So these two terms cancel, and lo and behold, using this form, I get back what I expect. Okay. So we need to justify that this is the form of the inverse metric, and then this is what we're going to use later on in getting to our results. Okay. So we're going to start with what is perhaps the easy part of the story, and that is, can we get this expression from the geodesic equation? Okay? So here we go. First thing I'm going to do is I am going to go ahead and assume that I'm treating a massive particle, because after all, non-relativistic general relativity should be looking at the behavior of massive particles. So that means I can immediately replace my parameter lambda with proper time. We haven't really talked too much about this, but parameterizing paths that are not time-like. Remember, massive particles follow time-like paths. Parameterizing paths that are not time-like gets tricky, especially null paths, because the path length is 0. The proper time is not a good parameterization. But this is massive, so we can take the parameter to be proper time. And then our geodesic equation is just going to become d2x mu d tau squared plus, as usual, gamma mu rho sigma dx rho d tau dx sigma d tau equals 0. And I can simplify this to d2x mu d tau squared plus gamma mu 0, 0 dx0 d tau squared. And how do I justify that?
Some derivatives are a lot bigger than the...
Exactly. So I'm summing over rho and sigma everywhere it appears, but if rho is a spatial index, then the component here would be a dxi d tau. But we've already said that all of the dxi now these are taus, all the dxi d taus are way smaller than the dt d taus. So the only term I have to think about, the leading term, is going to be the one where it's dt d tau, because that is going to be the biggest contribution. Okay, moreover, because it's squared. Okay? So we might say that this results from A. Okay? But this guy, we can actually write. We know how to calculate the Christoffel symbols. And just using the expression that we know but tend to forget on a regular basis. Okay? So we have the normal expression for the Christoffel symbols in terms of the inverse metric and derivatives of the metric. And all I've done is said, I want the gamma mu 0, 0, so I've plugged in 0, 0 in all the appropriate places. Okay? Now we still have to sum over this lambda. But what can you tell me about these two terms?
I like 0 because we're taking derivatives of the metric, and we know that eta is diagonal and that the h nu mu pieces, even no matter where they are, as long as we're taking derivatives of them, should go away, right?
Actually, it's more direct than that. We're assuming a static field. So the time derivatives of everything in the metric should vanish. Okay, so these are each 0. They don't cancel or anything like that. Okay. This guy I can actually replace with minus d lambda h00, because g00 would be eta 00 plus h00, but eta 00 is a constant. It's minus 1. The derivative, that's going to vanish. So the derivative of g00 is really just the derivative of h00. Okay? And now I'm just going to plug in my inverse, my ugly ass inverse metric. This is by C, that we get to set those to 0. But you'll notice the second term combined with this is going to be order h squared. So we're going to disregard it. So we're just going to keep the linear term. So this is going to settle down to minus 1/2 eta mu lambda partial lambda h00. Okay. And now this is my Christoffel symbol. Notice it's got one upper index mu, and the other two indices are both lower and they're 0. This lambda disappears. So this guy I can take and shove him back into the geodesic equation. Okay. So with that in mind, I'm going to erase this, and I'm just going to go back to the geodesic equation. All right. Everybody on board? Yeehaw! Yeehaw! Come closer.
I see what you've done.
All right, yes, I know, it's perfect. Okay, here we go. So what we're left with is d2x mu, d tau squared. Actually, just let me erase this. Screw this. Give myself as much room as I can get. d2x mu, d tau squared. Where am I? Minus 1/2 eta mu lambda d lambda h00 dt d tau squared equals 0. Okay? How many equations does this represent? 4, because there's one overall index mu, so I can write this down for 4 different values of mu. Now, we don't really need to write down all 4 of them, but it helps to look at what the time-like component looks like, and then what a spatial-like component looks like. We don't have to do all 3 spatial-like components, they'll all look the same. So let's start with the time-like component. So if the index mu is 0, then this just becomes d2t d tau squared, because x0 is time, minus 1/2 eta 0 lambda d lambda h00 dt d tau squared equals 0. Okay? But eta 00 is only non-zero when lambda is equal to what? 0. This is diagonal. This is the metric, the inverse metric of Minkowski space. So this guy I can set to 0, which means this should be 0. But what can you tell me about that? It's 0 because everything is static. Oh yeah. Okay, if d0 g mu nu is equal to 0, then that means that d0 of this and d0 of this is 0. There's no time dependence anywhere. So this whole term goes away, and the geodesic equation reduces to that. That actually tells us something useful. What it tells us is that we can reasonably parameterize our space or our path by a proper time that is just equal to coordinate time. If I take this and I take 2 derivatives of t with respect to tau, I get 0. I could use any linear combination, okay, any linear function of tau, but we might as well just look at the simplest one. Now, should we have expected this? Yeah, in non-relativistic physics, time is actually a useful parameterization of paths. We were forced to give it up and use something a little bit more slick in relativity, okay, because of the relativity of time, but in a non-relativistic setting, we should be able to reliably use time to parameterize motion, and that's what we just found, okay? So now we turn to the spatial part of this equation. And if I just write down what that looks like, d2 xi d tau squared minus 1/2 eta I lambda d lambda h00 dt d tau squared equals 0. Wait a minute, hold on. Do I need to write this? No, because we just decided we were going to set tau equal to t. So that I don't even really need to write. If this is I, what does lambda have to be? I'm not flipping you off, I'm waiting for you. It has to be I, okay. But what is eta I?
1.
It's 1. This is just it's a component of the inverse metric of flat space, but it's a spatial component. The time component would be -1 and then 1, 1, 1. So this is just 1, so let's just erase that. Okay. Oh, sorry, this should be t. Okay. Well, what is this? That's the ith component of the acceleration. Yes, the second derivative of the position. So this is ai, and so this says that this is equal to 1/2 di h00. And now I'm going to do something that looks like a total cheat. What I'm going to do is say this is minus di of minus 1/2 h00. And then I'm going to use this as my definition of phi. Okay? And if this is confusing, this index could be up or down. Technically, when we erased that eta I, it was grabbing this lower index and raising it. But these are spatial derivatives in Cartesian coordinates in flat space, so the index being up or down doesn't matter. Okay? So what I've just found, if I extend this to all three components, is that the acceleration is minus the gradient of phi, which is one of the things we're looking for. Now you might say, well, wait a minute, you cheated because you had to make this definition. But is that really a cheat?
We just found out how the metric connects back to Newtonian stuff, right?
I know, but I mean, it looks like I just made this choice to cook the books to get it to what I want. Like, why does it have to be this and why not like just h00? Like, that seems like a way. Well, the thing is at this point it is kind of arbitrary, but we have a second thing to check, and that includes phi. So we better be making the exact same identification here when it comes to figuring out how phi is related to the metric. And in fact, we will, okay? So even though this might look a little bit arbitrary right now, it is constrained because you have to be using the same definition of phi in both of these expressions, okay? We good? All right, yes, I know. It's the most exciting lecture in this class ever, and you can't wait for spring break. Neither can I. Okay, here we go. Almost there. Not even finished on the thing. Almost scared. Okay, so what I've got to do now is I've got to tease this guy out of Einstein's equations, but it turns out that in order to even get started, we're going to have to rewrite Einstein's equation a little bit. But we're going to do it in a very useful form that we will see in applications many times in this class. So if I take Einstein's equation, so that's Einstein's equation. And what I'm going to do is I'm going to rewrite it in something called trace reverse form. So let me just show you how you get to this. First of all, I'm going to take the trace of both sides of this equation. Now we've learned that the trace means you actually hit it with the inverse metric, because what it does is that for every tensor, it raises the index and makes them the same. And that's what a trace is in this class. And if I come through here and do this, this guy becomes the Ricci scalar. Oh, sorry, I should be using the metric g, not beta. Sorry. So This guy just raises, this is the Ricci tensor, it raises one of its indices and it sets them the same. That's the definition of the Ricci scalar. What's g mu nu, g mu nu? It's 4. Both of these are the same as both of these. So if one is the same, you get the identity, but then you're tracing it, so you get 4. So the 4 divided by 2 gives me a 2. This is still the Ricci scalar. Hey, look at that. That's easy. That's just minus r. And then the right-hand side just gives me 8 pi g times t. So what I can do with that is say that r, whenever it appears, can be replaced by minus 8 pi gt. Okay, r minus 2r is minus r. That's the left-hand side. And then the right-hand side is 8 pi g times the trace of t. But if minus r is equal to this, that. Okay, it's algebra. But now what I'm going to do is take this expression and I'm going to plug it back into the original Einstein equation there. And so I'll now have r mu nu minus 1/2 g mu nu times minus 8 pi g t is 8 pi g t mu nu. Okay? You can let your minus and minus give you that. Okay? And then you can just move this whole thing over to the other side. So what you've done is, in the original form of Einstein's equation, where you had 2 curvature terms and 1 energy momentum term, you can exchange with this trace reverse form to have 1 curvature term and 2 energy momentum terms. Okay? This is called the trace reverse form of Einstein's equation. What's incredibly useful about it is that it dramatically simplifies Einstein's equation when you have no sources present. Because if you have no sources present, both of these are 0, and you just have r mu nu equals 0. In the original form, if you take away the sources, you get that r mu nu minus 1/2 g mu nu r equals 0. And it's kind of hard to see how that's equivalent to this. It is, but it's not obvious. Okay? For our purposes today, though, you'll understand why we're going to use the trace reverse form in time. Okay? There is a cheat here, though, and you should be aware of this. The unknown here, when you want to solve this equation, is the metric. Okay? And so we often say, you specify the energy momentum, the right-hand side, and then you solve for the metric. But the metric is hiding on this side, too. Because you had to use the metric in order to get the trace of t. So it's still a very complicated system of equations with the metric popping up in all kinds of weird places. All right, but for now, that's going to be the form of Einstein's equation we're going to work with. And then to really make use of this, the first thing we have to do is specify some source. Okay. Now, in non-relativistic physics, if we're looking at an energy momentum tensor, in non-relativistic gravitation, the only thing that sources gravity is mass. Momentum doesn't give you gravity. Energy doesn't give you gravity. Electromagnetic fields don't give you gravity. In general relativity, all of that stuff contributes to the curvature. Okay? But if something is moving and has momentum, it contributes to the curvature. The momentum does, in addition to the mass of the thing. But in Newtonian gravity, it's just the mass of things. Moreover, we want those things to be stationary at rest. So our energy momentum tensor actually dramatically simplifies. That's the only non-zero component. Because all of the other components have to do with momentum or motion, and we don't include those as sources in Newtonian gravity. So the only non-zero term is T00, and it happens to be equal to the mass density. Okay? So I don't know how you want to write that so that you actually realize the rest of it's 0. There you go. Okay. So I'm going to erase this for a moment. I'm sure I'll need it in a minute. But we've got to calculate. So this is T mu nu, but we have to calculate the trace. To calculate the trace, we've got to take the inverse metric times T mu nu. This is part of the trace reverse form of Einstein's equation. And so now plugging in our inverse metric, The only term that's non-zero here is t0, 0. So that means I can, in this equation, replace mu and nu with 0 everywhere they appear. Okay? This is just 1, or sorry, minus 1. And then these are only non-zero when alpha is equal to 0 and when lambda is equal to 0. Eta is the inverse metric of Minkowski space. When they are, so this is going to be non-zero only for eta 0, 0, eta 0, 0, but each of those are minus 1. Doesn't matter, they're squared. So this is going to be minus h 0, 0 times rho. Okay. So that is my trace of the energy momentum tensor. Notice, it's a bit odd, right? If I handed you this matrix and I said, what's its trace? You might be tempted to say it's rho. You just add the diagonals. But that's not the way we compute traces. We compute traces by raising an index and identifying the two. But to raise that index, you have to use the inverse metric, and that's where we're bringing in this h0, 0 term. Okay? All right. So now we can go back to the trace reverse form of Einstein's equation, and I'll see if I can fit it in up here. So the right-hand side of the trace reverse form is 8 pi g t mu nu minus 1/2 g mu nu t. Okay. And it turns out the only term that I need to focus on is the 0, 0 term of this, so I'm going to just set all these equal to 0, 0. And then plugging in what I have for this. So this is the right-hand side of the trace reverse form. We'll come back to the left-hand side in a minute. The left-hand side is r mu nu. Okay, but the right-hand side is the source term side. So plugging in what I have 8 pi g. This is just rho. And then I just said what t was, and I've already forgotten it. It's good of me. Minus 1/2 g 0, 0 minus 1 minus h 0, 0 rho. Okay. G00 is what I get when I put 0, 0 right there. So that's 0, 0 there, that's minus 1. And 0, 0 there, that's plus, yeah. I'm not done yet.
Why are we only focusing on G00? Why don't we consider...
In this expression,
Yeah, why don't
we're going to get what we need out of this one expression. There's other stuff in the other expressions, but we're going to get the thing we need out of this one. Okay? And let me write down the rest of this, and then you can. Okay, I mean, you're free to explore those other expressions and see what interesting, fascinating things they tell you, but we're going to get this out of this expression. Okay, there you go. So this is just a little bit of algebra at this point. So rho minus. So the minus 1 and the minus 1 is plus 1, so minus 1/2. And then I'm going to have a, this is the sum and difference of, well, this will be 1 minus h squared. Okay, see, minus 1 plus, minus 1 minus. So the cross terms will vanish is what I'm saying. The h00 squared term we're going to ignore because it's higher order. That is not rho minus, no it is, it's rho minus 1/2 rho, sorry. Yeah, I'm missing a big parenthesis down there, that's why I'm getting confused. Okay, so we get 4 pi g rho. Okay, there we go. Hey, look at that. Boom. Now we've got to do the left-hand side. If the left-hand side gives us del squared phi, we are golden. Not in golden, we're golden. I'm glad you didn't laugh at that. That was your lame test. If you had laughed at that joke, you are definitely sucking at the teacher. You know how I said this is going to be a 45-minute lecture? This is going to be by the skin of my teeth. All right. Okay, here we go. The left-hand side, again, I'm just focusing on the 0, 0 term. So, of r mu nu, I just want r 0, 0. To get r 0, 0, we go back to the Riemann tensor, remembering that the r 0, 0 is the full Riemann tensor contracted over the upper index and the middle lower index. And then these, if this was mu nu, this would have been mu nu, but everything is 0, 0 now. And then digging into our definition of the Riemann tensor, remember this is just a bunch of derivatives of Christoffel symbols, etc. Just throwing that expression down, we have d lambda, gamma lambda, 0, 0, minus d0, gamma lambda, lambda, 0, plus gamma lambda, lambda rho, gamma rho, 0, 0, minus gamma lambda, 0, rho, gamma rho, lambda 0. Holy cow, not a lot of stuff. Okay. Big step. The gammas are built out of derivatives of the metric. The metric does not depend on time. Okay? So the derivatives of the metric aren't going to depend on time, so d0 of that should be 0. Okay, that's by C. These are all going to be of order derivatives of the metric squared. But that's quadratic, we're ignoring those. So we're going to ignore those by B. So the only term we need to worry about is that guy, the leading term, and then banging him out in detail. We're going to have that guy plus spatial derivatives. Okay. Again, all the gammas don't have time dependence, so this guy is 0. And then this guy, we can write using the definition of the Christoffel connection. And so this term is going to become partial I times 1/2 gi lambda, partial 0 g lambda 0, plus partial 0 g 0 lambda, minus partial lambda g 0, 0. Okay? And we know this is 0 because nothing depends on time. This is 0 because nothing depends on time. So the only guy that survives is that one. So I have g di 1/2. This is only going to be non-zero when lambda is equal to I. So this is going to be g I partial I g 0, 0. But what is GII?
-1.
It's 1. These are spatial. Okay, so that guy is really just 1. If I move the 1/2 inside of, oh wait a minute,
So they don't have to.
the derivative of g 0, 0 is really just the derivative of h, because this is constant. So I might as well replace that with an h. And then I have di. Sorry, this should have been raised. I have di minus 1/2 h 0, 0. If I just move the minus 1/2 inside of that derivative. But this is, that's del squared. That's minus 1/2 h 0, 0. What did we identify minus 1/2 h 0, 0 as? Phi. We've got the left-hand side. Okay. That's it. I'm leaving. Bye. Gotta go catch a plane. All right, I'll see you guys Tuesday. I sent some emails out trying to confirm